Okay, we left off last time in Chapter 12 having discussed the basics of electrical transport. Today's lecture is going to continue on where we left off last time, and we're going to focus on semiconductor materials exclusively. Now, semiconductors, there's typically two classes. There's what's called intrinsic semiconductors, and there are extrinsic semiconductors. For the sake of this class, we're going to consider intrinsic semiconductors as meaning pure or undoped, the stoichiometric material. Now, if we dope it, meaning we exchange some of the atoms with something else intentionally to modify its electronic properties, that would be extrinsic, and we'll give you some examples of those in a minute. Some things to recognize about intrinsic semiconductors, that they typically have a band gap less than 2 electron volts, and they commonly consist of group 4 elements, so silicon or germanium, for example. However, they don't have to be stuck with group 4 elements. You can have a mixture of group 3 with group 5 elements that overall start to look a little bit like group 4 elements. This can be gallium arsenide, indium antimonide, and many others. You can also have 2,6 elements. So overall, it's 2 plus 6 equals 8, the same as 2 4s, right? That's like cadmium sulfide or zinc telluride. So as we go from group 4 to 3,5 and eventually 2,6 semiconductors, we're increasing the electronegativity difference between the two atoms, and therefore it's becoming more ionic. As it becomes more ionic, this is going to change its electronic properties. It's going to become a stronger bond, and this generally leads to a larger band gap. As you increase in the degree of ionic bonding. And this then, of course, leads to more insulating properties, since the only difference between a semiconductor and an insulator is the size of the band gap. Right? So intrinsic semiconductors, we mentioned this last time, but they can have both holes in the valence band as well as electrons in the conduction band. If it's an intrinsic semiconductor, we're going to assume that the concentration of these two is roughly equal. So you have the same number of holes as you do electrons. Okay? And this is because we create holes by promoting an electron from the valence band up to the conduction band, so it leaves behind a hole for every one electron that gets promoted, so they should be roughly equal. Now, just a reminder on circuits. If you have a circuit like this and you have a battery, from the positive end of the battery, a current will move through the load, through our resistor, and it'll head towards the negative side of the battery, so positive and negative. That is the current. But the electron flows are opposite to that. Electron flows this way, and our holes move in the same direction as the current. Okay? Perhaps one of the easier ways to think of semiconductors is to picture them as all silicon and then imagine what's happening with the bonding electrons. So we're going to draw that. We'll draw a lattice of silicon, silicon bonded to silicon, bonded to silicon. And since we remember that silicon crystallizes in the diamond cubic structure, we know that every single silicon is bonded to 4 other silicons. So you have bonds, which are 2 atoms shared. These are single bonds. So these atoms are shared between these different silicon atoms. And by sharing, they're able to fill their octet and have 8 electrons each, which is what they would like to have. So all these silicon atoms, 8 electrons each. Finish filling this out. Okay, now what happens if we provide a little bit of thermal energy? We can actually take one of these electrons and remove it. We can knock it out. Even though it wants to stay close to the silicon, it can temporarily escape. So we're going to remove our electron here. We're going to place it right here. There's our negatively charged electron. It leaves behind a positively charged hole where that electron used to be. And now, if we have an external electric field applied to this, you'll have remembered in physics that if you apply an electric field, that it's going to accelerate your particles. This hole is going to move in the direction of the field. It's going to travel that way. And your electron is going to travel in the opposite direction of the field, this way. Okay? Thereby, if you just simply remove one of these electrons from its site, then it costs energy to do that. It's not necessarily a huge amount of energy, but it costs some energy to do that. And then you have 2 carriers that are able to carry electricity through this. Now, what if it wasn't heat that caused this? What if it was light that caused this? We had a photon of light coming into our sample. It hit that electron and interacted with it. how much light would it take? Well, what would be the energy of the light required to cause that temporary separation? Well, we know that because we know the difference in energy between the valence band and the conduction band. So this, again, reminder, is our filled valence band and our empty conduction band. This is the band gap, Eg, which in silicon, I think we said was about 1 electron volt. 1.1 electron volt, so around 1 electron volt. Therefore, our energy of our light must be at least equal, must be greater than or equal to the band gap energy if it's going to cause this promotion. And we remember how to calculate that. We call this h nu, or hc over lambda. That's how we're able to calculate the energy of the photon. So we could right now calculate the energy necessary of the light to promote that if it was 1.1 electron volts. Let me grab a calculator and we'll do that. Okay, when we plug that in for hc over lambda, we remember that our general expression for this was equal to 1240 nanometer electron volts divided by the wavelength equals the energy in electron volts. So in this case, when we plug it in for 1.1 electron volts, we find that the wavelength is equal to 1,126 nanometers. Okay. Now, electrical conduction can arise in these semiconductors due to both the motion of the electron traveling to the left as well as the hole traveling to the right. How does the hole travel? A good way to think of that, I think, is just to picture what's happening. As this electron is able to hop and fill that gap, now this becomes the hole, and so forth. And so then this next one over could fill that spot, moving the hole here. So hole motion. Whereas the electron is not hopping from an existing site to existing site. Think of it as being in the conduction band, where there are plenty of empty seats for the electron to be able to move through the conduction band. It's not hopping from occupied site to occupied site. It's on a whole new other level, which we call the conduction band. Therefore, the total electrical conductivity should take into account both contributions from the electrons as well as the holes. So just like we did last chapter, or last video, we said that the electrical conduction due to electrons is N, that's the concentration of electrons, multiplied by the charge of each electron, multiplied by the mobility of the electrons. But now we're going to add similar terms for holes. Here's our concentration of holes and our mobility of holes. Now, we've already mentioned if it's an intrinsic semiconductor that N equals P equals Ni. Okay? Now, that doesn't mean that the contribution from holes and electrons have to be the same. They don't contribute the same amount because they don't have the same mobilities. They have different mobilities. And we will not cover in this class why that is, but there are future courses that you can take if you're interested in learning about why different carriers have different mobilities, basically why they should interact differently with their surroundings. Therefore, if N equals P equals Ni, we can simplify our expression to this, which we will underline, where the only difference is the mobility of the holes and the electrons. Now, extrinsic semiconductors are those which have been doped intentionally to modify their electronic properties. And we can have both N-type and P-type extrinsic dopants. What do we mean by that? N-type means that we've doped it such that it intentionally has far more electrons than it does holes. If it's an intrinsic one, it has equal amounts. And now if it's P-type, then we have doped it such that it has far more holes than it does electrons. So how do we do this? Let's consider N-type doping. What we're going to do is we're going to add an impurity that has an extra electron, such as phosphorus. Right? So we're going to start by drawing our same lattice that we had before. So silicon atoms. But this time we're going to replace one of the silicons with phosphorus. So let's take this one out. Take this one out actually. Okay, so that. We'll put phosphorus here, and we're going to put silicon here. Now, most of the silicons have 2 electrons. as we drew before. But phosphorus has 5 valence electrons, and we know that by going to our periodic table, and we can take a look and see where phosphorus is. It's a group 5 element, whereas silicon is a group 4 element. So here's our group 4 elements. Silicon, it has 1, 2, 3, 4 electrons, whereas phosphorus is group 5. It has 1 extra electron. It's got 5. So if we go to our picture, it might look something like this, where it has an extra electron that isn't tied up in bonding. Extra electron. It isn't tied up in bonding, so that means it's not going to be quite as tightly held as the other ones. That doesn't mean that it's not tightly held at all. Well, after all, phosphorus has 15 electrons, so it must have 15 protons, and the proton-electron interaction is still going to be one that wants to hold it, but it's not going to hold it quite as tightly. Therefore, this electron is free to move, easily ionized. Ionized means it is taken away from the phosphorus, so it can become a free electron. To become a free electron. Okay? Now, when it leaves, phosphorus then becomes partially positively charged. It's just lost an electric charge of the negative variety, so it must become positively charged. Now, just like we can do this with phosphorus to make something N-type, we can also make it P-type by adding something that is missing an electron, say boron. Boron, rather than having 4 valence electrons, it only has 3, so it's missing a spot. It already has a hole built in. And this hole, just like the electron is able to move, because it's not bound very tightly, this hole is not able, it is now able to move because it's not bound very tightly, leaving the boron atom left behind partially negatively charged. It's going to have a negative charge. So whenever you dope something with extrinsic dopants, it takes a little bit of energy to steal away the electron or the hole that it donates, and then once you do that, you leave behind a charged ion. Okay? So we would say that the P-type is, the phosphorus causes N-type doping, and the boron causes P-type doping. And we could obviously do this with much more than phosphorus or boron. We could just take a look. Here's our group 4 elements right here. And if we wanted to do a P-type, we could do boron, aluminum, gallium, indium, and so forth. And for N-type, we could do phosphorus, arsenic, antimony, these group 5 things. Okay? Alright, that is extrinsic doping. We've said that it leaves behind a charged donor or a charged acceptor afterwards. Right? This boron is an acceptor for electrons. Right? Maybe it's useful to draw this same concept but using energy band diagrams. So how would this look from an energy band diagram perspective? Well, in our energy band diagram, we have our conduction band, we have our valence band, conduction band. We said that this was completely filled and this one is up here was empty. So what does this do? Consider first the phosphorus atom. Where would the phosphorus atom sit in terms of energy levels in this picture? Well, phosphorus is a donor. It's a donor that doesn't take much energy to strip away this electron up into the conduction band. Therefore, we're going to consider it as an impurity state. We're going to say this is the impurity state. Phosphorus impurity state. That site used to have an electron, but that electron hopped up here to the conduction band, and it didn't take much energy. We're going to say that this delta energy equals small. Small compared to the overall band gap. On the other hand, if we have boron, what does boron look like in this picture? Boron looks like this. It's an energy level down here where we started out with these were filled. Our electron used to be down here, but it hops up slightly to fill this site and leaves behind a hole. So here's our hole left over. Whereas up here, we have our electron created. So you can see that by extrinsically doping something like silicon with phosphorus or boron, we can increase the number of a certain type of carrier, and this becomes very important for electronic devices. Okay? And by doing this, we can have conduction at a far lower temperature than we would normally need. Normally, we needed to cause conduction in silicon, we needed to overcome this entire band gap energy, and that was large, so it took a large amount of thermal energy. But look, for these dopants, we only need to overcome very small energy. That's called the ionization energy. How much energy does it take to strip away the electron or to cause something to accept an electron? Right? And it's not very large. So from this, we can now modify our conductivity. We can say if something is heavily doped one way or another, for example, let's say we added lots and lots of boron. So we added many electron acceptors and we created lots of holes. In that case, the number of holes, P, is going to be much greater than N and Ni. So we can say that this one is, all of its electrical conductivity is essentially going to come from the holes. Whereas up here, we're going to say, because we doped it with phosphorus, that N, the number of electrons, is going to be much, much greater than P, or the intrinsic number of electrons that are present. Therefore, all the conduction will come from the electrons, right? And so we can modify our expression to say it's essentially just equal to either one or the other. Of course, this is technically plus whatever value is coming from the intrinsic case, but oftentimes that's very small compared to the extrinsic case. So for p-type extrinsic semiconductors, we'll say that the dopant impurity has an empty spot. It can accept an electron, boron, aluminum. We drew the picture of this, and we could imagine, based on what we drew here, again, what the band diagram looks like, and we have a good feel for what the conductivity of it should be. Again, this technically should be plus the intrinsic values. It's just that this is typically much larger than this is, and so we often leave it off. So, what should the temperature dependence be for semiconductors? Here's a plot showing the number of carriers, Ni, versus temperature. Remember, I represents the intrinsic scenario. So this is how many electrons and the electron concentration that's intrinsically being created just by heating something up. Now this is plotted on a logarithmic scale over here, and this is regular axes here for temperature. You can see that we're seeing a dramatic increase in electrons as we heat this thing up, right? They're thermally activated processes. Therefore, if you want to make an intrinsic semiconductor conductive, you need to heat it up. Intrinsic semiconductor must be heated. Must be heated to be conducting. It typically takes a fairly large amount of energy because you're overcoming a large band gap. Okay? Now, we can actually generate, if we were able to plot, since this is going to be a thermally activated process, and it's going to depend on the energy required to overcome the band gap, we can treat that much like an activation energy. If it takes electrons that much energy to be promoted from the valence band up to the conduction band, that's essentially our activation energy. Therefore, we can say that our conductivity should be proportional to the exponential of our band gap divided by kT. Let's see, pause one moment. Okay, that's right. So it's proportional to that. The actual expression is going to be the conductivity is going to be proportional or equal to n, a constant, multiplied by exponent of negative band gap divided by 2 kT. We introduce a 2 because we're exciting for every one electron that we create, we also create a hole. So we're getting double the conductivity. So we have to include both of those. And that expression is given here. Therefore, if we wanted to make this expression look linear, we could do the same things that we've done previously. We would bring large N over, take natural log of both sides, plot it against 1 over t, or in this case 1,000 over t in this plot, and you see that it should obey a linear trend. From that linear trend, we could calculate the band gap, and we'll have a chance to do that in class tomorrow. So a question we might ask ourselves, true or false? An extrinsic semiconductor will not increase electrical conductivity with increasing temperature at all temperatures. What should this one be? To answer this one, we have to remember what? We remember that it takes thermal energy for intrinsic semiconductors to become conductors, right? They have to overcome a very large band gap. But extrinsic semiconductors, they only have to overcome a very small energy, and once they overcome that small energy, they become completely ionized. And so because of that, once they overcome a small energy, they've already picked up all the electrons that they have to have available, and therefore it's no longer going to increase in conductivity. It's going to be flat until we start to overcome the band gap, and then it's going to increase. So this one's a little bit challenging. We'll talk about it tomorrow in class a little bit more. The answer here is false. They don't increase over all temperatures. They're going to be flat over a period. Now here's a diagram that might help explain it. Here's our electron density plotted against temperature. This is a log plot over here. And our initial material has these conditions. Our initial material has a number of donors, 1 times 10 to the 17th donors per centimeter cubed. Remember that a donor is something like phosphorus that's donating an electron. Now, if we go back and look at our scenario, if you start out with that, and then we start to vary the number of acceptors, things like boron, by the time we get to Na equals Nd equals 1 times 10 to the 17th centimeter cubed, then we have the same number of acceptors as we do donors. Therefore, our overall doping is intrinsic. They cancel out. The acceptors cancel out with the donors, and it just looks like an intrinsic material. And it increases at this normal rate, which we just showed you in a previous plot. However, if our number of donors does not equal our number of acceptors, in fact, if we have more donors than acceptors, take a look at what happens. We start to have excess electrons left over, right? Because now there's more donors than there are acceptors, therefore we have leftover electrons. So if we have 9 times 10 to the 16th for our acceptors, we have some electrons left over. If we have this, 7 times 10 to the 16th, so even fewer acceptors, that gives us more electrons, and so forth. Until for this black line up here, the number of acceptors is much less than the number of donors. And see how the temperature dependence changes from this region, roughly, let's mark it, from that region until roughly this region. This temperature region has no T dependence. Right? In that temperature region, we don't need any more thermal energy to ionize our donor electrons. We do, however, need thermal energy down at very low temperatures. This region is called freeze out, meaning if you get cold enough, even your easily ionized electrons from the phosphorus atom can't escape phosphorus. Going back to our picture, even though phosphorus has an extra electron that it's not hanging onto very tightly, it is still hanging onto it. It still has, if this was like a planet, it'd be like the moon still experiences some gravitational pull to the planet. It's going to take some energy for it to be pulled away. This is experiencing an electrostatic attraction to the phosphorus atom. It takes some energy to strip it away. So if we go to low enough temperatures, we take away all that thermal energy, it cannot escape the phosphorus and it stays stuck to the phosphorus. If it stays stuck to the phosphorus, then it's not free to move into the conduction band and give us conductivity. Therefore, if we were to plot electrical conductivity instead of electron density as a function of temperature, it too would drop to 0. It would plummet because there's simply no carriers available. And this doesn't matter how many dopants we have, they all freeze out at low temperatures. And then, just like they freeze out at low temperatures, at high temperatures, they're already ionized in this medium region, and then at high temperatures, this is what we call the intrinsic region. Intrinsic. So in this case, in this picture, we added 1 times 10 to the 17th centimeters cubed of donors. However, once we get above a certain temperature, greater than the band gap, basically, it starts creating its own electrons, and it doesn't need donors to create the carriers. And so it starts to dominate, and it starts to look like an intrinsic material. See how all these lines merge together? And it starts to behave just like an intrinsic semiconductor at high enough temperatures. Okay? We will talk more about that in class tomorrow. So the electrical transport of semiconductors can be separated into these 3 regions: freeze out, extrinsic, intrinsic. What about mobility? What factors influence mobility? First off, dopant content. If something is heavily doped, then it's going to leave behind lots of acceptor ions or donor ions. These are things like the boron minus or the phosphorus plus. After they have accepted an electron or donated an electron, they are now left over in the lattice, and nearby electrons that pass by, instead of just passing by normally an electron, it will interact with that. It might be attracted and temporarily stop there, or it might be pushed away by the boron that has an extra negative charge. And there's some really cool tools we have that can help calculate what mobility should do. For example, BYU down south has a clean room tool that you can go to, and you can calculate what the resistivity should be as a function of doping, as a function of temperature, and it will actually generate some values. So this is a very useful tool that you can use. So it requires significant amount of impurities to reduce mobility. So if you only have a few donors or acceptor ions in your lattice, they're not going to dramatically reduce mobility, but they will if you start to add enough of them. And now temperature, on the other hand, temperature can play a much larger role on changing your mobility. Here we see, plotting electron mobility on the y-axis against temperature, that all these things with temperature start to go down. So as temperature goes up, mobility goes down. And this should make sense. As atoms start to vibrate more and more, they start to bump into the nearby passing electrons or holes, slowing them down, so they experience more of a friction force, and they must slow down, right? Let's talk about the Hall effect. The Hall effect is an important measurement that we make because it tells us whether or not our electrical conduction is coming from holes or electrons. Why can't we just use electrical conductivity? Right? Electrical conductivity tells us how much electrical current is able to move through our material, but since both holes and electrons are equally capable of carrying electrical current through our material, we can't differentiate which one's coming from which if we don't do a Hall measurement. So how does a Hall measurement work? It goes back to principles that you learned in your Physics 1 class. Basically, it looks like this. Imagine that you have a long, skinny sample like that, and you're going to pass a current through it. Your current is moving this way. That's your current. So it's going to pass from the top of this purple sample down to the bottom. Now, if current's going that way, that means electrons are going this way. Electrons go that way. Read this Hall voltage by simply applying a magnetic field. If they apply in a magnetic field vertical, then the right-hand rule says if our current is moving that way, right, and we have a magnetic field pushing it up, then it must experience a force that pushes it one way or the other, right? It must experience a force that way. So we're actually going to have our electrons move in this material. They're going to be pushed to one side or the other. And in doing so, it's going to create a voltage from one side of this to the other. We measure that voltage, and depending on the sign of it, we know whether or not the electrical carrier in this system was dominantly electrons or holes. So this Hall voltage, when we actually go to calculate this to figure things out, we say that the Hall voltage will be equal to RH, that's the Hall coefficient, multiplied by I, the current, multiplied B, the magnetic field, and divided by T, the thickness. So we've already said that the magnetic field causes charged particles that are moving to feel a Lorentz force, and so they get pushed to one side of the material or over the other. This RH, the Hall coefficient, is equal to 1 over n, the number of carriers, divided by their charge. Therefore, we can not only calculate what type of carrier is present, but we can calculate how many. So this is a great tool to measure the number of free electrons or free holes in your material, which is important for electrical conductivity properties. Okay, we're almost done today. The last thing that we're going to talk about is semiconductor devices. Semiconductor devices, we're only going to cover a few of the basic ones, and these are critically important. They're small, they have low power consumption, they can be cycled back and forth very rapidly. One of the most important ones that is the most basic one, really, is just what's called a PN rectifying junction. A rectifier, if you've ever used it in your ECE class, a rectifier takes a signal that is AC and turns it into DC. So it takes an alternating current, something like this, where we have your current alternating back and forth, and it says I'm going to switch that so that we only have left over the positive portion, then nothing, and the positive portion again, and then nothing, right? It's cutting out the negative portion of the signal. That's important for a lot of applications. For example, many of our electronics don't require AC power. They require DC power. So you have to have an inverter or a rectifier. You have to have a rectifier that's going to take the AC power from the wall and turn it into DC power, which is what you're going to use in your device in many instances. To make this happen, we're going to use what's called a p-n junction. Just like the name sounds, it's going to be what happens when we mix both a p-type material and an n-type material. So we take literally one block of material, which is p-type, and we're going to sandwich it up against another block of material, which will be n-type. Now, why do we do this and why does it matter? It actually changes quite a bit. Think about it. Let me bring this up a little bit. Since the p region has excess holes and the n region has excess electrons, if we were to put a voltage across this junction, both of those carriers will move. Okay, let's draw our holes here. Here we have excess electrons, right? Now, think about what will happen if we try to move the carriers such that the holes move this way and the electrons move that way. What will happen? Well, a hole is just the absence of a free electron, and a free electron is just something that's been taken away, so it's created a hole. So if you push these into each other, they're just going to cancel out. They're actually going to recombine and annihilate, and they'll do so continuously. Meaning if you try and push current this way through the material, current this direction is not possible. Because for every hole that you try and push to the right, you have an electron going to the left, they just recombine, so it's not possible. However, if you try and go the other way, it works fine. I think a useful way of showing this is in terms of our energy band diagram. Over here we have our p-type material. In a p-type material, this is our conduction band, this is our valence band, and because it's p-type, we have lots of holes left over in the valence band. As we try and force them this way, we over here have conduction band electrons, and we're trying to force them to the left. They're going to recombine. Our holes and our electrons recombine, and they give off light. So if you've ever heard the word LED, or a light-emitting diode, that's exactly what this is. It's just a P and an N-type material sandwiched together, and we're forcing current the wrong way, since current can't go through, and it's just causing recombination of holes and electrons. This gives off light. And then even better, we can change the color of light that gives off, because we know that energy is not destroyed. Therefore, if this is the band gap, and it's equal to, let's say, something like 3 electron volts, well, what color of light should that give us? We can calculate it. We would say Hc over lambda, right? And that's 1240 electron volt nanometers divided by lambda. When we punch that into our calculator, we can now calculate what color of light that ought to be by figuring out what the wavelength is. So 1240 divided by 3, that means that our wavelength of light is 413 nanometers. So lambda equals 413 nanometers. And then we just pull up our electromagnetic spectrum, and we double check what light that corresponds to. Light wavelength spectrum. And we're, 413, so we can double check roughly what that would be by pulling it up. And it looks like 413 nanometers is right here. That's actually probably just in the purple. That would be like a purple colored light, right? So if you wanted an LED that was purple, you would choose a band gap that has band gap about 3 electron volts. That's a pretty big band gap, right? If you wanted something with a different colored band gap, you'd calculate what wavelength of light you're interested in, turn that into an energy, and get a material that has a band gap near that energy. That's the basic principle behind LEDs. Now, there's a lot more to LEDs, where you have more than one species that's giving light off. Instead of just the band gap, you can have things that luminesce or phosphoresce, and we won't be covering that in this lecture today. Okay, but that's the basic idea. If you try and move a current to make electrons recombine with holes, you get no current. But if you try and move it the other way, then you have no problem. Therefore, going back to our original picture, we said that if we want to rectify a current, for example, go from positive, negative, and only keep the positive part, then we'd simply put this together in a way that didn't allow current to go backwards. So our negative voltage produced no current. It would just give light off instead. So we've made a rectifier. There's many other devices that we can create that are based off of similar p-n junctions. And I'm not going to go into too much detail. I don't expect you to understand all of these. You've probably seen some of it in your ECE class. We're just going to go through the main ideas right here. One of the most important ones is a transistor. A transistor is used to amplify electrical signals or to act as a switch for storing data. They can do a lot of other things, but those are some of the main reasons why we use them. And there's two different types. There's a junction transistor and a MOSFET. Let's talk about a junction transistor first. This is used to amplify a signal. Now, transistors always consist of an emitter, a base, and a collector. Emitter, base, collector. And if you look at our band diagram below, you see that the emitter, in this case, is an N-type material. I mean, it's got lots of free electrons in the conduction band. Reminder that the conduction band's up here, the valence band is here, this is our band gap. Over here in our P-type material, what's going to happen is, since it's P-type, it has mostly holes in the valence band, and then over here since we have an N-type material for our collector, again we're going to have electrons up here. Now what happens here is if we apply a voltage, we apply a driving force, say we apply an electric field this way. If there's an electric field that way, these electrons want to move this way. Okay? Some of them, upon going from the N-type to the P-type, this looks a lot like the rectifying junction from our last problem. Some of them are going to recombine. Some recombine. But the trick is to make this region, your base region, as thin as possible. You make it very thin so you don't get too much recombination. And then the ones that are able to make it through that region without recombining, then they go and they drift into this collector region. And this drop in energy due to the voltage that you have applied to it is a big drop, so they go downhill in energy. So they're strongly accelerated through there. And in doing so, they amplify the signal. The voltage is increased here. So schematically what this looks like, here is our input signal. This could be the electrical signal coming from your guitar, for example. You take your guitar cable, it's creating a small amount of an electrical signal. You plug it into your amplifier, and you want to amplify that signal to make it sound good. So that small signal starts out here. You apply a voltage from here over to here, and so you're going to start moving electrons this way to the right. Electrons want to start moving that way. They have to make it through the P-type region, and if they do, then you have a much larger signal. This is what the amplifier is applying, a much larger voltage, which then really accelerates them to your output signal. So your input was small, your output is very large. And this is made possible by understanding electronic properties of materials, how conduction band and valence bands work, how recombination works, and we won't go into more detail than that. That's really the basis of it. Again, the catch is that this base region is thin, and that you have a small voltage at first driving it across, but you have a large voltage driving it into the collector region. Okay. Another type of transistor which we're going to talk about, and I won't show you the band diagram, I think it's too confusing for this class, is something called a MOSFET. MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. This type of transistor, we have billions of them in our smartphones on us right now. How it works is it creates a switch, something that's conductive under a certain scenario and not conductive under another scenario. Now, just like we said, the transistors always have to have a emitter, a base, and a collector. Another word for those, when we talk about transistors, is source, gate, and drain. So, if the flow of electricity in this diagram is from the right to the left, right, we would like to have electrons flow like this, but we only want to have them flow under certain scenarios, where if we apply a voltage right here, apply voltage, and then you get current. And if you don't apply a voltage, then you don't get current. Now you have a switch. This can be the basis of electronic memory or flash memory, right? Whether or not something is conducting or not. That can be a 0 or a 1 in terms of memory. So how does this work? If we start out with a P-type silicon substrate, then all of this material would have excess holes. Now what we do is we introduce small regions in the drain and the source, which are N-type. So in the N-type region we have excess electrons, Over here we have holes. So what will happen if we try and move electrons into this region where there's holes? They're just going to recombine, right? They're just going to recombine and we won't get any current passing through there. So it's initially set to off. If you don't do anything to the gate, it's initially set to off. But what can we do to this? Well, we can apply a voltage to this gate material, which has a metal, shown in blue here, and then it has this brown layer. That's the insulator. So going back to our name, metal oxide semiconductor field effect transistor. So here's our metal in blue, our oxide in brown, that'll be the insulator, and then down here we have our semiconductor. What this allows us to do is if we apply a positive charge up here, if we apply a voltage such that we pull a positive charge here, that will temporarily create negative charges in this channel, which if it's negatively charged, now our electrons can pass through here, no problem, without recombining, because we've temporarily created a bunch of extra electrons there to satisfy the holes that would normally be present at that gate. If you take that voltage away, then this is no longer conducting and it goes back to its original state. So this is only made possible by us being able to accumulate positive charges here on the top side of the metal, or where the metal is, and negative charges down here on the bottom side of the insulator in the semiconductor layer. That property is called dielectric. A dielectric material won't allow current to pass through it, but it will allow the buildup of charge. And that will be next video's lecture. Okay. So transistors, to summarize, must have a source, a gate, and a drain. And then we have to have a gate and a gate insulation. And here's some text describing the basic operation. There are some differences between junction and MOSFET transistors. We won't go into the details of it. I think this is interesting though. When you start to put together these transistors in different ways, and maybe you did this when you took ECE, you can actually make logic. You can make logic operators. We know that computers have to be able to know what or and, or nor, or not, what these things actually mean. And we know what they mean because we have complex brains that can process that. But how do you make a computer process that? And you do it using a series of transistors put together in clever ways. And we won't talk about how exactly that works in this class, but here's the basic diagrams. So just to wrap up, maybe 5 minutes left, I'll just say that semiconductors really have been the basis of just incredible technologies. For example, thermoelectrics, I'll have this in class tomorrow. Thermoelectrics are devices that can convert a temperature gradient to and from an electrical current, and you can understand exactly how these work by taking a look at my website at eng.utah.edu/sparks. And then this is how do thermoelectrics work, and it's basically can be understood exactly from band diagrams. How is it that we can harvest waste heat and turn it into useful electricity? I'll have a demo of that in class tomorrow. A little more on this. How do we go about making these devices out of semiconductor materials smaller and smaller? Well, microelectric circuitry was no mistake. It was actually the result of a famous scientist named Richard Feynman, who in 1959, at one of the big material science communities, it was called the APS meeting, he gave a talk which is now famous called "There's Plenty of Room at the Bottom." And in this lecture, he basically said, we've got to miniaturize. We've got to start doing things at a much, much, much drastically smaller scale to make much more exciting technology possible. This was, I think, the beginning of nanotechnology. Now nano is such a buzzword, we're all used to hearing it. But he said we should be able to create nanomachines that arrange individual atoms in just the way that we want them. And he issued 2 challenges. His first challenge was for $1,000 for somebody to create a tiny robot. His second challenge was for somebody to write a book on the head of a pin. So the first guy won the first challenge. His name was William McLennan. He was actually a watchmaker. And, he won the challenge sort of on a technicality. He used conventional existing tools to make a very, very small robot, right? And so he was a watchmaker. Unsurprising, he knew how to work on a small scale, but he kind of was a technicality. Feynman was thinking much smaller. How do you go dramatically smaller? But the second challenge was actually won by a graduate student named Tom Newman, which I think is exciting. You guys are, undergraduates, and the graduate professors, their advisors probably take all the credit. But here's an instance where the graduate student had the idea. He was led to think that, okay, we can shrink text by instead of using pencil and pen or tiny little machines to write, what if we use something even smaller? And he actually used a beam of electrons to scale text down 1/25,000th of its original size, and he was able to write the first paragraph of the book, A Tale of Two Cities, on a pinhead using this electron beam. You can see it right here. It was the best of the times, it was the worst of times, and so forth, right? That's on a tiny, tiny, tiny scale. So this idea put forward by Richard Feynman that there's plenty of room at the bottom, that we can do incredible things by shrinking down how we think of material science, has led to incredible things. Circuits, lithography, e-beam lithography, the fact that computers used to be the size of large rooms, and now in our pocket, every one of us has a smartphone which is more powerful than the greatest supercomputer ever made at first, is really a sign of what miniaturization has done. There's a concept called Moore's Law, which has been that we're going to try and keep on making things smaller and smaller and faster and less and less expensive. So the general rule said that there would be a doubling of the number of transistors on an integrated circuit every 2 years. Now we predict that the 5 nanometer transistor will probably be the limit to traditional transistor miniaturization, that we cannot get smaller with existing materials. And because of that, Moore's Law, which is held for so long, is actually already starting to slow down. We're approaching the point where we're going to need material scientists and people with innovative, exciting, completely out of the blue ideas to come up with new ways to store information, memory, to process and perform computer logic operations on an even smaller scale if we want to continue to see dramatic improvements. Some of these ideas are out there. We have researchers here at the U, for example, that are exploring spintronics, which is storing memory in the momentum and the direction of the spins present in materials of individual electrons. So there's some exciting areas out there that are going to require new and exciting innovations in materials. So it's an exciting time to be working electronic materials because of just the sheer opportunity to make really mind-blowing new innovations. So that's all we have today. I will pick up next time. We'll cover more dielectric materials and piezoelectric materials, and we'll finish up chapter 12.